Hi, this is John Isles and welcome to Geometer's Paradise. We're looking at Activity 4 from Lesson 2-4, Angles Formed by Lines. In this case, we want to show that vertical angles are congruent. And we're going to begin with this drawing and identifying the two sets of vertical angles. Now, vertical angles are across from each other. They share a vertex but no other common points. So ACE and DCB are vertical, angle ACE and angle DCB, and ACD and ECB are vertical, angle ACD and angle ECB. Alright, so our goal is to show that vertical angles are equal to one another. So let's start with that first statement. Show that angle ACE is equal to angle DCB. Right, we begin by doing a linear pair. See, we want to build a connection. We want to find some way of making these two angles equal. And what we know from the linear pair work we've already done is that linear pairs sum to 180 degrees. So I can take these two, DCB and ACD, which form a linear pair, and these two, ACD and ACE, which form a linear pair, and I can manipulate the equations to show that these angles are equal. So let's start with our linear pairs. Angle DCB plus angle ACD is equal to 180 degrees because they are a linear pair. And I can say that angle ACD plus angle ACE is equal to 180 degrees, again because they form a linear pair. Now, I'm actually going to rearrange these lettering, the lettering here. I'm gonna write it a different way. I'm going to write ACE plus ACD. This is just for the sake of illustration. Look what's happened here. We have an equation with three pieces, two angles, and 180 degrees. And here we have an equation with three pieces, two angles and 180 degrees. In both equations, 180 is common and ACD is common, which means that the remaining piece has to be the same. Alright, and what we're going to do is we're going to connect those pieces using the 180s. See, geometry is a little weird. We don't always substitute for numbers. Instead, substitute numbers into equations. Sometimes we substitute expressions for numbers, which is kind of counterintuitive compared to what you might be used to in algebra. Here we see the 180s, and as geometers we just start to drool a little bit. We're going to substitute for those 180s. Angle DCB plus angle ACD is equal to angle ACE plus angle ACD by substitution. And then we say, hey, look at this. I've got ACDs in both parts of the equation. That means I can subtract them out. Doesn't matter that they're not numbers. So DCB is equal to angle ACE by subtraction. And that is our goal, more or less. We actually were interested in ACE equal to DCB. We're backwards, but by the symmetric property we can just turn that around. So that's one set. We can't actually say that vertical angles are congruent though, because we only have one of two possible sets. In order to cover all of the bases, we also have to do the other set. So we need to show that angle ACD is equal to angle ECB as well. We do it exactly the same way that we did it up here. So I'm going to go ahead and just kind of copy this and then wipe out this first statement. So we're continuing our proof, and now we're doing ACD and ECB. So we're going to connect them through a common linear pair as well. ACD and DCB, DCB and ECB. So angle ACD plus angle plus angle DCB is equal to 180 because of the linear pair. And angle DCB plus angle ECB is equal to 180, again because of the linear pair. We see the 180s and we make our substitution. Angle ACD plus angle DCB is equal to angle DCB plus angle ECB by substitution. And then we subtract out the DCBs so that angle ACD is equal to angle ECB. Subtraction. Alright, and this means that we are ready to make our result. Since both sets of vertical angles are congruent, I know I said they're equal. Equality and congruence are synonymous. Since both sets of angles, vertical angles, are congruent, we can say that all vertical angles are congruent. And that proves our theorem.